This problem's got quite a bit of stuff going on here. It's going to be longer than some of our other quizzes that we have done. But let's go ahead and look at it. We've got steam that's entering the first stage turbine that's shown here. Pressure is 40 bar, temperature is 500 degrees Celsius. It's got a volumetric flow rate, remember that's A times V, which is 90 cubic meters per minute. Now that steam's going to exit that turbine at a pressure of 20 bar. Temperature is 400 degrees Celsius now. So notice it was reduced. And then after that point, it's going to be reheated. So we're going to send it through this reheater here. And it's going to have a constant pressure. It's going to be reheated to 500 degrees Celsius. Then, notice the pressure is still 20. Then it's going to go into this next turbine. Now at this next turbine, we are going to have it leave as saturated vapor at a pressure of 0.6 bar. We're going to have steady state operations. We're going to ignore the heat transfer from the surroundings and everything, and also kinetic and potential effects. We want to find mass flow rate of the steam. Notice the units here, it's kilogram per hour. We usually don't have per hour. And B, we want total power produced by the turbines. Then finally we want the rate of heat transfer to the steam flowing through the reheater. That needs to be in kilowatts. So quite a few things to look at. First, let's do mass flow rate of the steam. Now, notice here we've got 0.1, here's 2, 3, and then 4. Now remember, before you start, you should always make sure you notice your keywords. We've got steady state. We're ignoring this stray heat transfer. The steam is going to be reheated at a constant pressure and leaves the second stage as saturated vapor. Alright, so those are going to be important terms to pay attention to. Now, since it's steady state, we know for our mass flow rates that the mass flow rates are all going to be the same, right? So we can say M1 dot equals M2 dot. That's got to equal M3 dot, which equals M4 dot. Let's just call it M dot. That way we don't have to worry about those subscripts. Now the equation for mass flow rate is rho A V, where V is velocity. We can rewrite that as volumetric flow rate over specific volume. Now this volumetric flow rate was given to us at this entrance right here. That means if we can find specific volume, that we can find M dot. So specific volume, you go to the table. You're going to look up these conditions. So your 40 bar and your 500 degrees Celsius, and then see what you got. Now it told us steam, so you can pretty much assume that's superheated vapor. You always want to double check, but in this case it is. So if you look on your table at a pressure of 40 bar and a temperature of 500, you're right here. So 0.08643. That'll be our specific volume number. Let's write that down. Let's just put V1 there. So that's 0.08643. That's cubic meters per kilogram. Now with this, we've got all the values we need for this calculation. So we'll put M dot. That's going to be the 90 cubic meters per minute. Put that over specific volume. Value we just found, that's cubic meters per kilogram. Now we're here. Now do we want to leave those units? Cubic meters goes away, but that's going to give us kilograms per minute. That's not what we want. We want kilograms per hour, so we need to convert. So we'll do 60 minutes per 1 hour. That'll take minutes away, and then that'll get the units we need. So that is 62,478.31 kilograms per hour. Alright, this is the first one right here. Now we need that. Now, we're going to use this later on typically we don't want to have hours in here, so I'm going to go ahead and convert that over to seconds. So kilograms per second, that's 17.36 kilograms per second, in case we need it later on. Alright, so now we've got that. That takes care of part A. Now we got to do part B. This one wants total power produced. Remember, power is W dot. And we have the energy balance equation that has W dot in it. So that is the equation we will go to. And it's steady state, so left-hand side is 0. So we'll have 0 equals Q dot minus W dot plus the summation of your inlet terms. So that's MI dot times HI. You would do this for each inlet. And then we would subtract the same thing but for the exits. So ME dot times HE. Now we've got two inlets. Let's see. We've got an inlet right here, and then we've got an inlet right here. We're ignoring this reheater right now. Control volume will just be these turbines, essentially. All right, we'll get to the reheater later on. So only look here. So we've got the two inlets right there and there, and then we've got the two exits. So there's one here and then one here. All right, so part C, we'll worry about the reheater. For now, we only care about the turbines because we're looking for the power. With that, let's go ahead and write these out instead of having the summations. So we'll have 0 equals QCV dot minus WCV dot plus M1 dot H1, because that was this inlet, and then our next inlet is this 0.3 here, so we'll have plus M3 dot H3. Now we're going to subtract the outlet terms. We have one here at 2, and then we have one here at 4, so we'll have minus M2 dot H2 minus M4 dot H4. And then we can simplify this. We already said all these mass flow rate terms are the same, so we can just call them M dot. And then let's group up the positive and negative terms. So 0 equals Q dot minus W dot plus M dot times H1 plus H3 minus M dot times H2 plus H4. So now we're left with that. Is there anything we can get rid of in that equation? Yep, this right here is going to go away because it told us to ignore the stray heat transfer. So we're going to get rid of that term. Now this W right here, since our control volume has both turbines in it, this is going to be the total power. The other way you could work this is if you wanted to just have your control volume be each of the turbines separately. You would just do this equation 2 times. One for this turbine, one for that turbine. Find W dot for each of them and then add them together. So either way you want to do it. It all depends on what you're picking for the control volume. Alright, so back to this. These values are going to come from the tables. Alright, so you're going to have to figure out what tables you need. So H1, we already said that was superheated vapor. So go to your superheated vapor table, look up this combination of pressure and temperature, and you're going to get 3445.3 kilojoules per kilogram. Now H2, for that one, you are at a reduced pressure of 20 bar and a temperature of 400 degrees Celsius. So if you look in your table, you will find that you're still going to be superheated vapor. And just to show you that, let's pull this table out. So this is our saturated water table. Our pressure is now 20. The saturation temperature is 212.4. Our temperature is 400, so we are well above this, so we've got to be superheated vapor. Right. So you're going to go to the same table you used for H1, and then look up this new combination of pressure and temperature, and your H value then will be 3247.6 kilojoules per kilogram. Now it goes through this reheater and then it comes back out. The pressure is now 20, temperature is 500. Notice the temperature increased even more. That means we still have superheated vapor. So all three of these are going to have the same table. This one will be 3467.6 kilojoules per kilogram. Finally, we're up here at 4. That says saturated vapor, so you're going to switch to the saturated liquid table. And then you look up this pressure, and you'll be able to find your H value. So here you'll get 2653.5. That's kilojoules per kilogram. Right, so if you're using the tables I'm using from that Moran book, these first three are A4, this one goes to A3. Now we're going to take these values, plug them in here. That'll give us 0 minus W dot plus 17.36 kilograms per second. That was this mass flow rate. And then just start plugging in your enthalpy values. H1 is 3445.3. Add to that H3, so 3467.6. Both of these are kilojoules per kilogram. Then we're going to subtract the outlet terms. So we'll have minus 17.36 kilograms per second times H2 plus H4. So 32.47.6, and then plus 2653.5. And these are both kilojoules per kilogram also. So now you're left with that. Alright, now if you look at your units, kilograms goes away. You're going to be left with kilojoules per second, which makes sense for units of power. Now just solve for W dot. WCV dot then is going to be 17,564.8. That's really kilojoules per second, but we know that that is equivalent to kilowatt. So your answer will be 17,564.8 kilowatts. Notice it is positive. If it's positive, you're generating power to send out of the system. Okay? So that is perfect. If you got a negative, you know you did something wrong. Part B is done. That was the long part. Now part C. This one we want to find the rate of heat transfer to the steam flowing through the reheater. Now our control volume is going to be the reheater. Alright, so we've got that. And for this one, you're going to do the same thing. You're still going to use your energy balance equation, but now we're only looking at the reheater. At this point, we don't care about those turbines. Okay, so we just care about this. So our pressure is 20 bar, temperature is 400 degrees, and then we leave at the same pressure, 20 bar, and then our temperature is now reheated back to 500. This is 0.2, that's 0.3. Write your energy balance equation. We'll have 0 equals Q dot. Whoops, this is a minus W dot plus M dot times H2 minus H3. And at this point, all we need to do will be plug in values. We're solving for this. Now for a reheater, does it say anything about power being required or produced? No, so we're going to get rid of this term. So that goes away. All we need to do now is plug in these three values. All right. So your Q CV dot then is going to be 17.36 kilograms per second times 3467.6 minus 3247.6. Notice kilograms goes away, so that leaves you with 3819.2 kilojoules per second. We want it in kilowatts. So we get 38, 19.2 kilowatts. Right. And it's positive. So if it's positive, that means our system is gaining energy from heat. All right. So positive makes sense in this case.